So we're gonna see how long we can go in this live stream. I've had my internet cutting on and out, in and out for the past half hour. So if we end up getting completely dropped, we'll just switch to shooting me emails, and I'll try to see what I can do in terms of my phone. So I didn't receive any email questions. Are there any questions for anyone out there who's listening? Gonna take that as a no. Well, here if you got any questions. Discussion board for today. Yes, we can. So let me bring it up. And I'll give you a quick look at it. So the question on the discussion board, oh joy. So you have to give it just a minute. It's currently in the process of trying to crash. So the discussion board asks, we have a reagent. We will know if it's inherently stereospecific, and if it's not, can we make it specific? So the SS here is stereospecific. So we have PBr3, that's blue ribbon, or phosphorus tribromide, sodium chloride, thionyl chloride, SOCl2, phosphoryl chloride, I think that's what that's called, KCN, and then actually, sorry, let me reorder these to make them a little bit closer. So you can see them all. NaCl, CO2, CO3, KCN, and fossil chloride followed by cyanide, or KCN. So the question is here, which of these are stereospecific, if any? And so this is what it means by stereospecific. Will it always be stereospecific? Or are there situations where it's only stereospecific? So something like PBr3, phosphorus tribromide, that is inherently stereospecific. So if we have something like this chirality of 2-butanol, if we introduce the PBr3 to it, what we will produce is always the inverse symmetry. So for this one, if we add PBr3, we end up getting, every time, regardless of conditions, the bromine being with the opposite stereochemistry of the OH group. Now, NaCl, the nucleophile here is chlorine, and so this is not inherently stereospecific. And the reason it's not inherently stereospecific is that there's two ways the chloride here could replace like an alcohol or another alkyl halide, and that's SN1 versus SN2. So because this can go through an SN1 or SN2 pathway, the only time it's ever stereospecific is when we're in an SN2 scenario. So we can make it SN2 by changing, mostly just here by changing the solvent. So if we switch to a low dielectric constant solvent, something that's not very good at stabilizing the carbocation, and we work with molecules that are like primary alcohols or primary alkyl halides, we're likely to drive a reaction that's actually stereospecific. So how about thionyl chloride? Well, thionyl chloride is always stereospecific. So if we have an alcohol and we want to convert it to a chloride, so PBr3 converts alcohols to bromides, thionyl chlorides convert alcohols to chlorides, this is always going to see an inversion of symmetry. And the same thing's true for POCl3. It's always going to see an inversion of symmetry. Now, KCN by itself, potassium cyanide, is like sodium chloride. They're both anionic nucleophiles. And it follows the same thing. It's not always stereospecific because, again, we can go by an SN1 or SN2 pathway, and the only way to make this stereospecific is to go through an SN2 pathway. Now the last one, tolsyl chloride, TCCl, with KCN, that is actually always inherently stereospecific. So when we do tolsyl chloride, we end up forming a tosylic complex, and those always interact by SN2. So whenever we get any type of nucleophilic substitution with a tosyl complex, we always have to go through an SN2 mechanism, and we always do an inversion of symmetry. So that's how the discussion board works for this week. There are two that are not inherently stereospecific, and the reason they're not stereospecific is because they can go through either an SN1 or SN2. The only way to make them stereospecific is to create a situation where they are going through the SN2 mechanism. Other questions? So you can never replace a hydrogen on an alkane unless you're doing something like free radical halogenation. So when we do an S2 mechanism, we're always substituting off either an alcohol or an alkyl halide. Now for E1 versus S2, E2, we are removing a hydrogen, typically speaking. So, but again, we never are able to replace a hydrogen. We can eliminate it, we can add it, but we can't replace it. The CH bonds are too stable. So the importance of a carbocation is that we form it whenever we have a leaving group. So when we have a carbocation, let's say we have something like our alcohol, we add hydrogen to it, and so we end up forming and we end up breaking that bond, and we end up forming carbocation. So the carbocation is super important in terms of understanding the outcomes of certain mechanisms. So first thing, a carbocation is an electrophile. It likes things that are electronic, or they're negative or have lone pairs, And mostly we have anions that like to attack carbocations. So something like a chloride ion will attack a carbocation. Now, the other thing about carbocations is that they're trigonoplanar. And because they are trigonoplanar, there's no preference for one side or the other. So if you have a trigonoplanar molecule, let me build one really quick. So when you have a trigonoplanar molecule, so something like this, you can attack it from either side. There's no preference for the front or the back side. So if there was any stereospecificity here, when we begin the reaction, if we go through a carbocation intermediate, we inherently lose stereospecificity. So if we end up recovering a chiral molecule, or a molecule that has a chiral carbon on it, it will be a racemic mixture of both the S and the R enantiomers. Now, the final thing is that carbocations are inherently unstable. So they are what's considered a reaction intermediate. In principle, you can isolate them, but they go from primary to secondary and then tertiary. Now, primaries are the least stable of the carbocations, and I have videos. I've never heard a good explanation as to why primary is more stable than primary is less stable than secondary, which is less stable than tertiary. I think it has more to do with formal charge difference versus oxidation charge difference. Regardless, though, this is the least stable, and this is the most stable, and the secondary is intermediate. But because carbocations are unstable, we can also get rearrangement. So if we go through an SN1 mechanism where we generate a carbocation, if we have something like this molecule, so we start out with, let's say, 3-methyl-2-butanol, and we form this carbocation as part of the mechanism, we can get what's called a hydride shift. And in a hydride shift, the hydrogen will move over and swap places with the carbocation. And so if we get that switch, now instead of reacting at this carbon, our nucleophile is attacking this carbon, now they'll attack at that tertiary carbon. So we can also get this with methyl groups. So let's say we had this carbocation. Well, this methyl group can shift places with the carbocation, and we can get this molecule. And this is true for just about anything. If moving a sigma bond, so this is a sigma bond between these two carbons, results in a carbocation that's more stable than beforehand, we end up rearranging the molecule. So a big example that shows up in, I think, Chem 2, is we can actually get rings. So if we have our carbocation here, we can actually get the ring to move over. To give us a tertiary carbocation. So the carbocation has a lot of implications on the final stereochemistry. So if we have a carbocation, we're not stereospecific. We're going to end up with a racemic mixture of both R and S if we end up generating chiral center. We get rearrangement, so we can get hydride shifts, we can get methyl shifts, we can get any type of sigma bond shift that will result in a more stable carbocation. And on top of that, well, those are the big ones. We lose stereospecificity, and we also get rearrangements with carbocations. So that said, if you're going through a carbocation intermediate for something like a secondary or tertiary carbon, it's faster. So this is the trade-off. Even though we start getting issues of selectivity, we end up replacing this with speed. Something like an SN2 mechanism. For an SN2 mechanism, they go very slow, but you're guaranteed stereospecificity, and you're guaranteed that you're replacing the one group that you want to replace. Other questions? So that's a good way to think about it. So there's two ways. So that's why I had the previous discussion board. So in the previous discussion board, I had the solvents on top, and I had your reagents on the left. So your reagents are going to dictate whether it's E or Sn. So if it's elimination or substitution. Your solvents are going to dictate if it's 1 or 2. So if it's a unimolecular or bimolecular reaction pathway. And the full disclosure here is that it's a blend of both. This is the really obnoxious thing about organic chemistry, is that if you run a reaction, you're going to get elimination products and substitution products, and you'll get the SN1 and you'll get the SN2 and you'll get the E1 and you'll get the E2. The point is that when we do this, we want to dial it in to favor our preferred mechanism. But big picture, if you want to favor it, your reagent is going to dictate if it's E or SN. If we have a small molecule, this is typically going to favor substitution. If we have a big molecule, we're typically going to favor elimination. For solvents, if you have a high dielectric constant, this is going to favor the one mechanism, so carbocation. If we have a low dielectric constant, we're going to favor the bimolecular pathway too. And this goes back to stability. High K dielectric, I keep saying high K dielectrics because that's what I was taught. High dielectric materials are stabilize those carbocations, so it makes it more likely that they're going to form. Whereas low dielectric solvents, those are less stabilizing towards those carbocations, which means that you're more likely to not generate the carbocation. I think I said that right. Yes, they're actually available. If you go to the course website under the first test material, there's a table that gives you the dielectric constants. And I think the solvents are organized by their dielectric constant. The other thing is whether or not they're product or aproduct. So product, that means there's a free hydrogen, and typically our nucleophile is an anion. So if we have a free hydrogen floating or H plus floating around due to the solvent, that's also more likely to favor the SN1 mechanisms. So if you go with an aprotic low dielectric constant solvent, and those are typically like they trend together. If you're low dielectric, you typically don't have a labile hydrogen. You're going to favor the SN2. If you're high dielectric and you have an acidic, particularly if you have an acidic hydrogen, you're going to favor the SN1. And again, those tend to scale together. So water is a high dielectric constant solvent. It also has a lot of hydrogens. Something like tetrahydrofuran, THF, doesn't have any acidic hydrogens and it's a low dielectric constant solvent. Yeah, that material is always available to you. I don't see a reason to make you memorize the dielectric constants. And it does get kind of gray area, like, because you can see water is one extreme, and like I think DMSO is the other extreme, where it's got like double digit dielectric constant. If you're between the two, the other thing is that you need a material that's polar enough that it will dissolve some of these compounds. So while it's great to talk about like, well, we should run it in this solvent, if your material doesn't dissolve in that solvent, it doesn't do you any good. So if you have something like sodium chloride is not going to dissolve in something like ether. But ether is really low dielectric constant, which means that it's going to favor the SN2 mechanism. And this is actually why things like crown ethers were developed, is that they're designed to kind of like promote, um, they're designed to help salt ionic materials dissolve in organic solvents. Let me, hold on, bring it up on my side. It's probably at the, so scroll through that whole packet first. So in that table of common 1H, 13C, and IR values, at the bottom of it's also the dielectric constants. What in the world? Where are my solvents? Oh, I bet it's in the packets. I know I had a big packet of dielectric constants because I used to give it out on exams. What I'll do is I know I've got it somewhere, so I'll just reload it up to the course website. Also, to be honest with you, I emphasize this a lot more than the book does, and this is where the book kind of tends to be less practical in that regards. But yeah, let me check. I could have really thought I uploaded to the course website, but I can just upload it this afternoon. This is also something you can just Google. Like if you Google up solvent dielectric constants, you'll get, I think Wikipedia has a pretty good list. Other questions? You need to be more. So, what specifically do you want to be able to predict about them? Because there's a long range of reactions that they undergo. So, what particular reactions are you interested in learning about? Page 13 of the study packet. Whoa. Wrong class. All right, give me just a minute. So, an example for one of the questions on page 13. If we have something like SOCl2. SOCl2 always clips in a hydroxide group and replaces it with a chlorine. So the one thing we need to check on is if we see any stereospecificity. So if we see stereospecificity, so we see a wedge or a dash, that tells us that if we have SOCl2, we need to invert it. In this case, we don't. So the reaction just ends up producing this chlorinated species. So that's kind of why the discussion board is what it is this week. You need to go through and start memorizing these reactions. So it's not like you can derive a lot of this. You're going to have to go through and create flashcards of what the different reagents are and what they do. The only exception to this are nucleophilic reactions. So if you have something that is a known ionic compound, so your strong acids, HCl, HBr, HI, HNO3, HClO4, and the third one, H2SO4. Although more we're going to focus on these, or you have any type of ionic compound like NaCl or potassium iodide. These are where you're going to see the SN1, SN2 reactions, and that's just going to need to be where you keep an eye on the solvent. So these will undergo substitution, nucleophilic substitution. So whatever the anion is going to replace either an alcohol or an alkyl halide. And you need to determine if the solvent's appropriate for doing an SN1 mechanism, which if it is, you can get carbocation rearrangement and you can get, you'll get a racemic mixture when you're done. If it goes through SN2, if you have a chiral center, you're going to inversion the chiral center. But there's no deriving a lot of these. You're just going to have to look them up and write down what they do. But this is covered in the online notes as well as the book. Other questions? And just again, feel free to email me in advance or shut the discussion boards if you got questions. The hard part for alkyl halides and alcohols is now having to memorize all those reagents. But this is why the course is divided the way it is that we started out with characterization analysis. We moved into naming with the alkanes, and now with alcohols and alkyl halides, we're going to add reactions. But everything that came before it's still going to be in there. So the hard part for this material is the reactions. Can you predict the reactions and keeping track of the stereochemistry? So again, the discussion boards are meant to help with this and to emphasize the important parts of the material. How does solvent affect the mechanism? Because the mechanism is going to tell you whether you've got stereospecificity or not. How is the reagent going to affect stereospecificity? Because we need to know if we're drawing wedges and dashes when we're done. And on top of that, you need to know if it's even relevant. So you can kind of see with the example I work, it doesn't matter. Even though thionyl chloride does inversion of symmetry, it's an achiral carbon, so it doesn't really matter whether it was wedged or dashed. And then if you can get through this material, alkenes is just the reverse of what we're doing right now. So it ends up, material actually ends up getting easier as we get past exam 3. And alkynes, which is the last material we cover, and ethers, those are pretty like, alkynes are alkenes with an extra bond. And ethers are super boring. other questions? Is there any general feedback from the first lab report that we should take into consideration with the second one other than our individual feedback? I would focus on your individual feedback. I also offer to review a draft in advance, so if you want specific feedback on this one, get it to me about 4 or 5 days in advance, and if I've got the time, I'll take a look at it. But generally, the expectations are pretty much the same for all. There's slight variations depending on the lab, but again, I try to set those up with the model lab reports that are on the course website, and also with your previous lab report. If you click on the assignment, you can see I individually wrote down wherever I took off points. So if you can open up your old assignment, it'll actually go through and there's comments in the text to sit back and say I took off points for this or I took off points for this, and also to kind of give you feedback. There are some things where I may not have taken off points this time because it was your first lab report, but I may take off points the next time, because you should kind of know it at this point. But in terms of the first lab reports, I mean, I think the lab was the bigger limitation of what, like, yeah, I think the lab was the bigger limitation with the previous lab reports. Like, the labs, if it had been a better lab for doing the lab report, they would have been better lab reports. But I would say in very few circumstances was it like I really didn't have that many bad lab reports in the last set. But again, because we were trying to get everything out of the way in case we had to shut down for COVID, I picked a lab I would not have normally picked for doing a lab report. I am glad we did the dehydration of cyclohexanol for your lab report. I think that's a better one to do. There's a little bit more meat to that analysis. So in principle, they should be better. Yes, actually ACD ChemDraw. I'll send you the link in the chat. It's clunky, but it's free. My major criticism is that it is clunky. Like, it's hard to like kind of get used to working with it at first. Even working with it for years, like there's still little things I learned. That said, it has a clean tool, so it will actually like make your structures look nice. It has pre-programmed structures, so if you do something like cyclohexene, it's already got a cyclohexene ring as one of the default options. And basically you just copy the image and paste it into a Word document as a picture, and it tends to work just fine. But I highly encourage this one just because it is free. Other than that, PowerPoint. Yeah, you're welcome. Yeah, I think the only other option out there is ChemDraw, and I think ChemDraw still runs for about $2,000. Yeah, a basic subscription to ChemDraw is $600. I mean, it looks nice. That's why grad students tend to steal it. Other questions? I think we did look up the registration for Wake Tech. I'm teaching 2 sections of Orgo 2 in the spring and 2 sections of Orgo 1. So if you are carrying on to Wake Tech, we're doing the hybrid courses again, and we're doing still the 8 students per section. If there is demand, I may request that we flip it and do 3 sections of Chem 2 and 1 section, or 3 sections of Orgo 2 and 1 section of Orgo 1. We're just going to have to kind of base it on what demand looks like. So if you're not able to get into Orgo 2 and you really want to, shoot me an email just so I can kind of pass it on to the powers to be and say like, hey, we really need to switch. We need to create an extra section of Orgo 2. Right. Might be getting some people about to come crash this live stream. This should be entertaining, hopefully. Oh, hi. You come to announce your presence. Come here. There you go. Isn't that more fun than being destructive? Her name is Squeaky. And she is a brat. Oh, really? But you can tell by that sound she's making, she doesn't actually have a meow. She just kind of squeaks. But it's the witching hour for her. She'll destroy something for about 20 minutes and then she'll go take a 3-hour nap. I can tell. It's kind of hard to tell if she's a boy or girl because she's like 9 pounds of fluff. Oh, isn't that right? Oh, yeah. Right, ready to go back to your chair? There we go. Oh. You're just going to sit there and purr yourself now. All right, thanks for showing up. Those of you who showed up today, and again, if you ever have questions, feel free to email them. I'll try to answer them at the start. You're also free to answer them during the discussion boards. Otherwise, I'll sit here and play ambient music for you. All right, I will see you all next week. Thanks for showing up.